Hello students, in this new video lecture, what actually I want to discuss here is that lattice enthalpy, which is used to predict thermal stability of ionic solids. Right? In the earlier lecture, we have discussed in what way Kapuscinski equation is useful to predict lattice enthalpy of ionic compound theoretically when exact lattice structure or crystal structure is experimentally not determined. Only ionic radius are available, then we can estimate lattice enthalpy. So, lattice enthalpy is a very important parameter which is used to uh, uh, predict the thermal stability. Thermal stability means कि if we heat any inorganic compounds or ionic solids, then whether it is decomposed or not. So ionic compounds here, what we are going to discuss here is like carbonate and oxide, Li2O, right? And Li2CO3. So these are the two compounds which is formed through lithium cation, right? So which is formed through lithium cation and two type of anions, actually oxide ion O2 minus and another one carbonate ion 2 minus. As you know that lithium plus has size of 59 picometer, right? So it is the smallest size cation in alkali metal group first. And oxide ion, so it has size 126 picometer, 120 126 picometer, right? And this carbonate ion possesses ionic radii 185 picometer, means oxide ion is smaller than carbonate ion. Okay, so when lithium plus forms ionic compound like that, Li2O and Li2CO3, means in both compounds Li is in +1 oxidation state, but here there is a normal oxide O2 minus and here there is a polyanions. So normal anion and here is a polyanion. Carbonate is called, this is polyanion, polyanion. Okay, so suppose how we can prepare lithium carbonate, right? So lithium carbonate is a ionic compounds, so it is soluble in polar solvent. So lithium carbonate is formed through lithium hydroxide and carbon dioxide. So once it reacts with carbon dioxide, it forms lithium carbonate. Okay, so lithium carbonate Li2CO3 in solid state, if you heat this compound, then it will be decomposed. Li2O plus CO2 gas will be released, right? So this will be in solid state. Okay, so once this ionic compound lithium carbonate is heated, this will be decomposed into lithium monoxide, which is in a solid state, plus carbon dioxide. If this reaction is occurring in forward directions or it has weak tendency to form this compound, it will be decided by lattice enthalpy, right? So the lattice enthalpy of this compound and lattice enthalpy of this compound, and the difference of lattice enthalpy from this, uh, the lattice enthalpy of lithium monoxide and lattice enthalpy of lithium carbonate. So through the knowledge of lattice enthalpy of all the alkali metal carbonates, we can predict whether this uh, lithium monoxide or respective another monoxides of alkali metal cations, whether it is stable or not, right? So suppose uh, similar to lithium carbonate, we have sodium carbonate Na2CO3 in a solid state, and potassium carbonate, okay, in solid state, rubidium carbonate, cesium carbonate in solid. If it is heated, it forms similar to lithium oxide Na2O plus CO2, right? It also forms K2O plus CO2. It forms Rb2O plus CO2, right? And this forms CS2O plus CO2, right? But it is only possible if temperature is greater than 650 degrees centigrade in case of lithium carbonate. Whether sodium oxide, potassium oxide, rubidium oxide, cesium oxides are stable or not, it will be uh, estimated through the knowledge of lattice enthalpy, right? So from Kapuscinski equation, we can theoretically determine lattice enthalpy of lithium carbonate and lithium oxide, right? And similarly, we can also calculate for sodium carbonate and sodium oxide, and similarly for cesium carbonate and cesium oxide, right? So, so actually, what is the through the use of Kapuscinski equation, delta, suppose in case of in case of lithium 2CO3 delta HL, it forms C, it forms Li2O plus CO2, right, in gas. So this is in solid phase and this is also solid if it is heated. The lattice enthalpy of lithium carbonate, actually it is determined So in the next similar Na2CO3 solid, so delta HL delta Na2O solid plus CO2 gas, right? The lattice enthalpy of sodium carbonate, in this case actually theoretically we have calculated like that. 2732 2246, here delta HL 2246, right, kilojoule per mole, and for this sodium oxide 2732 kilojoule per mole, right? So what will be the differences of lattice enthalpy between Na2O solid and sodium carbonate? The difference of this value and this value, so that is difference lattice energy is actually 486 kilojoule per mole, right? So similarly we can estimate for Rb 2 CO3, which upon heating gives Rb2O in solid state plus CO2 in gaseous state, right? So this happens if it is heated 800 centigrade, greater than 800 degrees centigrade. This reaction occurs if it is heated greater than 1000 degree centigrade, right? So what will be the lattice enthalpy of this rubidium carbonate? Actually 1954 delta HL for this compound, and for this rubidium oxide 2316 delta HL बराबर, right? And what will be the difference? What will be the difference of lattice enthalpy between rubidium monoxide and rubidium carbonate? So it is 2316. Actually it is 362 kilojoule per mole. So what you are observing here is that from moving top to bottom, the differences of lattice enthalpy always decreases. From the calculation of sodium carbonate and sodium oxide, the differences of lattice enthalpy 486 kilojoule per mole. In the same group, bigger size rubidium carbonate and rubidium oxide, the differences of lattice enthalpy is 362 kilojoule per mole. And similarly we can calculate for cesium also. So I hopefully we can say that the value will be still lower than this. It means the stability of this monoxide is not so high. As you move from top to bottom, the formation of monoxide is not so easy because the differences of lattice enthalpy decreasing from top to bottom. It means that the lattice enthalpy for monoxide is low, or you can say that lower carbonates are more stable, and More stable means, so it has high melting points and high ionic characters, right? So high ionic characters means this is highly ionic and more electrostatic interaction in this case. So we need much more temperature, much more heat to break the this lattice, right? So from moving top to bottom of a alkali metal carbonates, actually thermal uh, lattice enthalpy decreases, right? From top to bottom, lattice enthalpy decreases in case of carbonate. Lattice enthalpy decreases, right? Lattice enthalpy decreases means lower carbonates are more stable as comparison to initial like lithium carbonates or sodium carbonates. Okay, lithium carbonates easily decomposes when it is heated at 600 degrees centigrade. It will give the product like lithium oxide and carbon dioxide gas. But sodium carbonate is greater stability than lithium carbonate, and potassium carbonate is still more stable, and similarly rubidium carbonate is more stable, and further cesium carbonate is more stable than the any other. So we can uh, we can put a series like lithium to CO3 is least stable. So and next sodium carbonate is little more stable than potassium carbonate, right? And then rubidium carbonate, and then cesium 2 carbonate. So thermal stability increases from left to right. Okay, so that is why Rb2CO3 always decomposes at more high temperatures, means greater than 1000 degrees centigrade. So in this way we can estimate the stability of any ionic compounds through the knowledge of lattice enthalpy, and which is calculated from the Kapuscinski equation, right, where experimental lattice structure is not known, only ionic radius are available as a data. So in this way we can say that lattice enthalpy gives us idea about the stability of ionic compounds, right? So higher lattice enthalpy means more melting point, high melting point compounds, hard compounds, right? So lithium to CO3 and CS2CO3. So here lithium plus is the smallest sized cation, and carbonate is the larger anion, right? And this is cesium plus, and carbonate ion is similar. So this is common. Carbonate ion is similar in both case, only metal cation is different. Here lithium plus and here cesium plus. So lithium plus has high charge density, right? It has high charge density and very small size, very small size, right? And it is large, large size in respective group and low charge density. Low charge density. Charge density means charge per unit volume. Charge density means charge upon volume, right? So, according to Fajan's rule, if cation is very small size and if it has a very high charge density, then it has high polarizing power. So, it has large polarizing power, large polarizing power. Okay. So, it has poor polarizing means weak polarizing power. Okay. So, high polarizing power means it can distort the structure of this carbonate ion, which is larger in size compared to lithium plus. So, once it is distorted the structure of carbonate ion, so it has some covalency, it has some covalent character. Ionicity decreases in this compound, means lithium carbonate is not pure ionic compound. It has some sort of covalent character also because of the polarization effect. Since this polyanion has high polarizability through the lithium cation, right? So the structure of carbonate ion is destroyed. So that is why it is easily decomposed at 600 degrees centigrade and it has minimum thermal stability. Okay, so it has minimum thermal stability means low thermal stability, low thermal stability. Okay, and in case of cesium carbonate, actually cesium plus is bigger in size, which has poor tendency to polarize this large polyanion carbonate ion. So it cannot easily destroy or break the structure of this carbonate ion. So it actually stabilize cesium plus stabilize carbonate ion. Here lithium plus destabilize carbonate ion, right? So because of small size, so according to Fajan's rule, lithium plus destabilizes carbonate ion, result in the poor tendency of stability, and cesium plus large in size, which is supposed to it will stabilize the carbonate ion, means there is identity of carbonate ion structure and identity of cesium as a cesium cation. So in this case cesium cation, it has Cs plus and carbonate 2 minus. So electrostatic force is poor, means it is easily converted in water Cs plus and CO3 2 minus. Because of weak electrostatic interaction between cesium cation and carbonate anion, so it is easily soluble in water. So it is easily soluble in water. Easily soluble in water means it has high density of cesium plus and carbonate ion, right? So in a solid state, So in a solid state, actually it is more stable, and in the solid state it is less stable because there is a covalent character and there is ionic characters. So from moving top to bottom in a group first of alkali metal, actually alkali metal carbonates, so the ionic character increases from top to bottom, right, because of lattice enthalpy and as per Fajan's rule. Okay, so depends on the polarizability and polarizing power of cation, the stability can be predicted in another sense, right? So thank you for listening this video.